the seminar for today. We have in our midst a very renowned researcher in the area of human factors and economics, and he's a professor at the University of Wisconsin-Madison, where he investigates issues of human automation interaction, particularly trust and automation. He investigates trust in domains such as UAVs, maritime operations, and deep sea exploration. His work involves assessing interface and interaction methods to enhance trust calibration. He is also a co-author of a very, very popular textbook used by all human factors engineers. It's titled Designing for People, an Introduction to Human Factors Engineering. His research has been funded by several federal and state agencies, including NSF, NASA, and companies like Toyota and GM. It's my honor to welcome Dr. John Lee. Thank you.
Thank you very much for the kind introduction. It's a pleasure to be with you. I'm sorry I'm not able to be there in person. It would be really great to meet everybody. And hopefully we'll have some time for discussion, and maybe I'll be able to see you towards the end of the presentation. As I go, please feel free to interrupt, put a message up in the chat if you have questions, and I'll try to attend to those and answer them as we go through. So I'll try to make it interactive, and if you are inclined, please do post questions and interrupt me as you choose. What I'll be talking about today is trusting automation, and I'll be talking about conceptual issues, but then also statistical techniques and addressing data dilemmas, situations with data that may not have obvious answers. And as a graduate student, you might look at those and be horrified and think, what do I do? Or you can look at them as opportunities to learn something new and maybe develop a different approach to thinking about data. And I'll be talking about two of those. One is, what do you do when you have data that is discrete in the sense of a response, and then a magnitude associated with that response? So people can respond or not, and if they respond, there's magnitude. Very common sort of data. I ran into this data and it took me about a year to figure out how to analyze it. So be thinking about that. I'll give the answer later. The second data dilemma is, what happens when you have a large volume of text data? Thousands or tens of thousands of responses. How do you quantify qualitative data? And I'll be talking about that in the context of trust and automation. Before I start, I thought I'd show you where I live. This is Madison, Wisconsin. This is actually my commute ride to work. It goes under a Frank Lloyd Wright building, beautiful building along Lake Monona in Madison. Gorgeous ride to work every day. Sadly, have not done that in over a year. So I'm looking forward to getting back to that shortly. So I'd like to start by acknowledging the help of the graduate students whose names you'll see on many of the papers referenced in this presentation, particularly Azadeh, who's now at Waymo, did her PhD in related work. Shannon, Morgan, who's now a researcher at—
Dr. Lee, sorry I'm interjecting. We're unable to see your slides if you're showing that.
Oh, they should be show. Yes, that doesn't help, does it? So sorry about that. I thought I had started sharing earlier. So, okay, so you can see my slides now.
Yeah, now we can see, thanks.
Great. Yeah, sorry about that. I managed to fail to unmute myself and not show my slides in the same presentation. Amazing. So as I mentioned, Morgan, she's now at Apple in the industrial design studio. Lucky her. Josh Domar just graduated. He's at Toyota. And Shiwan is at Waymo as well. And Irene is at Ford, just graduated. So sadly, all of these students have graduated, and except for this one, Minyao is still working with me on that project sponsored by NASA. And I'll also be talking about data that I was collaborated with JD Power to analyze. And then NSF and Toyota CSRC are the other sponsors of this work. So to start, one of the, I think, challenges, pervasive challenges these days is confusing automation. And we talk about trust as a way of understanding or coming to relate to automation that you can't completely understand. And so you have to rely on the automation in the context of risk and uncertainty. And this, I think, is particularly true of how we relate to what I've labeled here as sometimes semi-self-driving vehicles. These are the SAE level 2 or 3 or maybe 2.5 or 2.75 vehicles. So one way to think about this is thinking about the trustworthiness or the capability of the automation on the horizontal, and then trust on the vertical, and what you would like is appropriate trust or calibrated trust along the diagonal. And I think the risk is that you deviate from this center line, either trusting too much, and this is a situation with these semi-self-driving vehicles. Ideally, you'd be like this driver, hands on your knees, ready to take the wheel at any moment, eyes on the road to detect deviations or situations the automation can't handle. But this is maybe more the case. This is a Tesla driver on the road, and you can see kind of fuzzily the orientation of his head. He is apparently asleep in traffic. So this is one of the inappropriate levels of trust that can emerge with Teslas and other very sophisticated semi sort of self-driving vehicles. And an example of that is the Ntsb investigation of a fatal Tesla crash that occurred in 2016. And sadly, the vehicle driver was not attentive to the road, went underneath this semi truck. You can see a little dents on the side of the semi, and it just took the top right off the Tesla and sadly killed the driver immediately. What happened preceding that crash is sort of fascinating. This shows the timeline starting at 0 at the beginning of the trip and then ending about 41 minutes later with the crash. And the gray indicates the periods where the autopilot was active. So you see the vast majority of time the driver had the autopilot engaged. The little green slivers there are places where the driver had the hands on the wheel. So just a fraction of the time, hands on the wheel. And then the yellow indications were warnings to the driver, and then the auditory warning associated with many of those visual yellow warnings. So lots of warnings, very little hands on the wheel. And then if you see the last 6 minutes where there weren't any warnings, ended in the crash. So probably an extended period of eyes off the road, certainly mind off the road, didn't respond to the imminent crash and was killed. So this is a case where the driver over-trusted the automation because the driver felt, I think, secure and felt that the automation was trustworthy, didn't feel the risk. So this, I think, is common in life. Unlike these natural situations where our bodies are designed to feel risk intuitively. This is Alex Honnold scaling a rock face without any protection. If he falls, he has, I don't know, 10 or 15 seconds to think about it before he goes into the rocks thousands of feet below. So this is an extremely dangerous thing. Makes my hands sweat just looking at this. Our minds and bodies are tuned to attend to this sort of risk. We are not attuned to the sort of risk that we take on by giving over control to vehicle automation. I think that's one of the deep challenges. So how do we address this? How do we mitigate over trust and give people a better sense of the risks they should be attending to? I think there's three basic approaches. One is interfaces, displaying information. The second one is algorithms, changing the way the vehicle responds, and then potentially interactions. How do you shift control back and forth between the person and the automation? And I'll talk about the first one briefly. This is one way of changing the interface to mitigate overtrust. And I won't go into a lot of the details here, but just to say this is a fairly complicated interface that might reside on a head-up display or in the instrument cluster of a vehicle that shows the driver proximity to the vehicle head, the rate at which that's changing, the situations where your vehicle is not controlling as it should be. So as that triangle gets bigger and smaller and moves around the space, it's indicative of what's going on with the automation. So this makes the automation a bit more transparent, maybe conveys a bit more of the risk of the situation. In addition to this visual display, we also had an auditory display that changed its tone and loudness according to the proximity of the risk. And this seems to work. We compared the visual, that display, with a discrete visual, just a telltale that's common in most vehicles, and we see a benefit. When you have auditory information, it seems to provide a bigger benefit than the dynamic visual information. So if you have a sound that's continuously modulating according to the risk, that seems to get people to attend to the road and minimize time in the risky situation. That's what's indicated on the vertical there. And across the horizontal are just different situations that could challenge the automation. And so what we see here is one way to mitigate overtrust, and it's through this auditory display in particular. One of the downsides of this auditory display, as you can imagine, is its annoyance. So one way to avoid that annoying sound is to use algorithms. And here we try three different approaches. The lane centering algorithm, which keeps your vehicle in the center of the lane. This is how vehicles like Tesla work today. They drive perfectly until they don't. The second one is a lane keeping algorithm that doesn't strive to keep your car in the center of the lane, it strives to keep your car in the lane. So it will wander around a little bit, indicating that it's not the one in control. You're the driver responsible, not it, and you need to attend to its imperfect ability to control. And then the last one is adaptive algorithm that switches between lane keeping and lane centering according to the situation. So the switch to lane keeping indicates a degraded capacity of the automation or a degraded capacity of the person. If the person's looking away from the road, you can trigger it to go into this lane keeping mode. So that's the basic idea, comparing or shifting between algorithms as a way to mitigate overtrust. And in an experiment, we compared the adaptive and the lane centering, the adaptive being the one that switches between lane keeping and lane centering. And on the vertical axis here, we have proportion of eyes on the road. So how much time people are looking at the road, and then adaptive lane centering. And you can see a systematic difference. The adaptive people look to the road more than with the lane centering. The two graphs differentiate the instructions we gave to the drivers. On the left, we told the drivers that they were primarily responsible, which is the roughly equivalent to the level 2 SAE automation. The driver is responsible. On the right, on the left, the automation is primarily responsible. On the right, the driver is primarily responsible. And what's interesting here is if you look across those, there's no difference, or maybe there's a difference, but it's very subtle. And what this illustrates is the effective instructions may not be that persuasive to drivers. And so at least in our experiment, the instructions had little effect, but the algorithm had a substantial effect. So shifting now to the situation where we go from the semi-self-driving sort of self-driving cars, the level 2, level 3, where undertrust is a problem, or overtrust is a problem. I'll shift now and talk about situations where under trust is a problem. Driverless vehicles, vehicles that can drive themselves and allow the people to be passengers in the vehicle. And I would say that these driverless vehicles give life just in a variety of ways. One is they allow, as illustrated in this image, older people to maintain mobility, allow them to engage in social activities, activities of daily life like shopping, and getting out to see friends that they might not otherwise be able to do. Driverless vehicles also help people recapture the 26 minutes each way they spend commuting on average across the US. So a lot of life is lost just by sitting in your car in traffic. And we have a project with NSF looking at the future mobile office being in the vehicle where you can get some work done and maybe also get some relaxation done. So driverless vehicles allow us to give people life. So this is really important and will only be achieved if we can raise the trust to an appropriate level. So we'd like those highly capable vehicles to be trusted and used, but they may not be. They may be under-trusted. And so what we're looking at here is determinants of trust. We talked about the micro determinants previously in terms of the moment-to-moment attention to the road that can be influenced by the movement of the vehicle. What I'll talk about now is looking at the macro level, the reputational or social influence of trust that I think is also potentially important. And ways to mitigate under trust, I think you can look at interfaces, algorithms, and also the interaction. So I'll talk in more detail about that in terms of how we can look at behavioral indicators of trust in a driverless car, simulated driverless car. Here we have people sitting in the simulator, but as passengers in the vehicle as it drives through a series of intersections with and without stop signs, with and without cross traffic. So they go on a journey. They go on that journey with 3 different types of algorithms: aggressive, moderate, and conservative. And these distinctions are made in how the vehicle brakes to a stop in the case of the stop sign intersections, and then how it accelerates away from that stop. And for the intersections without a stop sign, all of these 3 algorithms are identical. They just keep going. So each person went on a series of 8 drives with the same algorithm on 2 consecutive drives, and this was counterbalanced. It was a fully within subject design with a total of 24 participants. And what we were interested in part, was looking at the distance between the manual and the automation speed profiles and whether that would account for the difference between people's trust in those in the different algorithms, in the aggressive, moderate, and conservative, with the idea that you might trust an algorithm that was similar to you in the sense of having a similar speed profile. And that difference in trust would be reflected in a behavioral input, in this case, accelerator and brake input. So we're looking at, instead of people rating their trust, they're expressing their trust through brake and accelerator input. So we told them to press the brake if you want to go faster, and not that it's going to directly affect, but just indicating to the algorithm that you want to go faster. It had no effect on the behavior of the vehicle. Likewise, if you want to slow down, press the brake if you think the algorithm should slow down. So this pedal input was a reflection of how they thought the automation was doing. It was not a reflection of their trying to override the automation. So what we're looking at here is the distance to the manual speed profile. And I show this in part to emphasize to everybody to think beyond a bar chart and mean values. I think it's really important to show individual data points. So each circle here is an individual's response. And then the spread of those encapsulated by the violin plot, that gray band behind, shows the probability density function. And then the sine element here is the distribution of the individual plots within that probability density function. And then the points, the means, are the black dots, and the credible interval, the posterior mean credible interval from the Bayesian analysis, allow you to see the distance between the mean values, or the central tendency. So this combined plot, I think, highlights some of the important elements of the behavior of the individuals in great detail. You can see the spread, you can see the individual responses in a way that gets masked with just the bar chart and mean values. And I show this because I'll be showing another graph later that looks really different. And the difference, I think, is maybe something we wouldn't have seen without this visual. One thing to note on the right, the no sign, no traffic, these are situations where the automation just went straight through. There was no response of the automation. And so you'd expect the mean value across all the participants, that black dot, to reflect that. Their distance on average was the same for all of the algorithms. Another notable thing is that the moderate algorithm was more similar than either the aggressive or the conservative algorithm to the individual's driving behavior. So you might expect that to be the, in a sense, most loved or most complied with, most trusted algorithm. So this is that graph that looks way different and really odd. So this is the brake pedal input. And what you see are a whole lot of responses down at 0, where participants were satisfied with the trajectory, didn't press the brake pedal. And then above that, you see cases where they did press the brake pedal. And when they did, there were differences in magnitude. And the data dilemma that I presented at the beginning is this: how do you analyze these data? And there's a couple different ways. One is to just ignore it and fit a regression model to the whole data set. And that would be, I think, really bad. You're violating all sorts of assumptions of normality. Another is you could split the data and do 2 analyses, one like a logistic regression on part, and then a normal regression on the continuous part. So if they responded or not, that would be one analysis, and then a separate analysis for the magnitude of the response. That might be okay. Or you could treat it as maybe 0 inflated Poisson regression or something. The problem with that is that it assumes a similar underlying process for the magnitude and the response or not, and that may not be a good assumption. So there's no clear way of how to deal with these data. One approach that I think is really promising is a 2-part or hurdle mixed model. And I'll go through that in just a little bit of detail because I think it's really cool, and I would encourage you to look at this because it's widely applicable to the data that industrial engineers, human factors people in particular, deal with. So it has 2 parts. The first part is the response, indicating a response or not. That's the Z value here. If person responded with a brake press, it gets a 1, if not 0. And then the second part, and that can be modeled as a logit function, so a logistic regression type approach there. The second part of this 2-part model is the influence on the response magnitude. So given that there was a response, what is the magnitude of the response, just as a linear regression? And the really interesting thing here is the U and the V, the UI and the VI, and that gives you the covariation of the random effects associated with the 2 parts of the model. So these 2 parts are coupled, and that allows you to assess the degree to which these 2 parts of the model represent separate processes or not. I'll show you in our case what happened. So what's interesting in this brake pedal input on the right is that people press the brake when there is no sign. So the sign, no traffic, there's still people there are people braking. They want to slow down on the right when the automation is not. So there's no reason to slow down. There's no stop sign. You can go straight through. But that's not how people behave. And I think that that's really important as we think about self-driving vehicles. We need to think about the sort of conservative approach that people take today. They might expect the vehicles to take a similarly conservative approach, braking, even though they don't strictly need to. There's no sign for the intersection. Okay, this shows accelerator input on the vertical, and like before, conservative, moderate, aggressive across the bottom. And what we see here is that kind of as we expected, the moderate has less accelerator input than the conservative. You can see that on the left when there's sign and no traffic. On the right, what's interesting here is that with the aggressive, there's less accelerator input. But remember, the automation across these three levels is behaving exactly the same in these no sign, no traffic situations. So people are intervening with the accelerator input, even though the behavior to the intersections is identical across the algorithms. So this shows that the influence during the signed intersections where the automation came to a stop, maybe more slowly with the conservative and the moderate algorithms, and then sped up more slowly. People are compensating, it seems, for that during the no sign and no traffic situations on the right. So that's, I think, a really interesting effect, sort of inertia of attitude that the vehicle isn't going fast. So looking at the details underlying this two-part model, these are the beta weights of the model. One specific line I'd pull your attention to is highlighted in blue. And what's shown there is that the accelerator input is influenced by the intersection. So this is the magnitude of the input is influenced by the intersection type there, but not its, I'm sorry, the tendency to respond is influenced by the intersection, but its magnitude is not. So if you look on the left, the response is substantially different from zero, but on the right, the magnitude of the response is not. So this is a case where I think different processes are underlying the behavior, and those different processes govern response or not. And then there's another process that governs the magnitude given that you respond. And so I think that that can be extremely useful in looking at behavioral data. So this idea of response or not, and then the magnitude of the response, that two-part hurdle model applies to a lot of cases, not just behavioral data in the car, but anytime you have a response to a signal, anytime you have a defect and you're looking at the defect, whether it occurred or not, and then how bad the defect was, a collision that occurred in a car, and then how bad the collision was if it occurred. So I think very common data that I was surprised it took me so long to find a method for analyzing it. So maybe I'll pause here. If there are any questions, I'd be happy to answer them. So if anybody has questions before I move on and talk about something a little bit different. Okay, great.
I have a question.
Yes.
In the study where you looked at the auditory displays and mitigating over trust, did you look at masking of any other auditory variables like music playing or being on the phone and what effect that might have?
It would be, you're absolutely right. Not only is it annoying, it's probably annoying because it's masking the sort of stuff you want to be listening to. You want to listen to the radio. You want to talk to your passenger. You want maybe on the cell phone talking to people. All of those are going to be competing with this sound. So if all you're doing is driving, this could be a great solution, but people do other stuff while driving, which may be a reason for having this in some sense. If you're on the phone and you've got this in the background, and then it comes to the foreground and makes you feel nervous, maybe that'll save
Right.
your life, right? But yeah, the other things that happen in the car, absolutely important. And that's why we really looked into the movement, the motion, changing the algorithm to indicate its competence. And that's a little less intrusive and seems to work out maybe as well, maybe better. Um, but my friends in the industry say that won't work at all either,
Yeah.
because people don't like driving a car that doesn't feel competent.
Yeah.
So, yep, great question. Thank you.
Thank you.
Okay, so what we're doing in terms of next steps is some work that I was tempted to present here. Josh Domeyer just finished his dissertation looking at the interactions between pedestrians and vehicles. So automated vehicles, how should they signal to pedestrians that they're slowing down? And what Josh found is that the proxemics and kinesics, the motion and proximity of the automated vehicles approaching a stop, can be really important to signal to the pedestrian that the vehicle is stopping, maybe more important than explicit signage or signals on the vehicle itself. So that's some work that he did and developed a beautiful mechanistic model, a differential equation describing the interaction between the pedestrians and the vehicles. So I won't be talking about that. Instead, I'll be talking about something completely different, looking at under trust through survey. So this is a online panel survey that J.D. Power operated, a tech choice study. And they had about 8,000 people, 8,500 people in 2016 and 2017 complete the survey. And I'm not going to talk a lot about the overall survey, but just one question, and that is, how much would you trust the ability of a vehicle equipped with self-driving technology to operate without a human driver's input? So this is level 4, level 5 automation, the Waymo vehicle. And this was published in Human Factors Journal last year. So if you're interested in this paper, like the one that I just presented, both of those were published in Human Factors and are available. And so this is another data dilemma. So if you have 16,000 survey responses, open-ended responses to this question that goes with the Likert scale, the rating that people gave, how do you deal with that? It's really hard to read that many responses and do qualitative data analysis on them, sort them into piles. And so what we did is we looked at them quantitatively and qualitatively, and this shows the quantitative analysis. So the percent of responses from definitely would not to probably would not, probably would, definitely would in 2016, 2017. You can see a similar pattern. A lot of people on the definitely would not, probably would not side with, you can see more people definitely would not in 2017. What happened in 2016? That Tesla crash that I mentioned. So can we get that out of the qualitative analysis? So one way to treat qualitative data quantitatively is with topic modeling. And topic modeling is a statistical technique that identifies distributions of words that go together, tend to occur together across documents that define coherent topics. Here's an example of some of those topics: gene, DNA, genetic versus brain, neuron, nerve. Different topics, different clustering of words. Those topics are distributed across documents. So a given document might talk about genes and genetics, another document about brains and neurons and nerves. Okay, so that's the basic idea of topic modeling. It allows you to look at probabilities of words across topics and probability distributions of topics across documents. So when we applied topic modeling to the J.D. Power data, we were able to identify a series of topics and their associated keywords. So topic 1 has high probability of having things like car, thing, wrong, safety, and I labeled this "Many Things Go Wrong." Okay, and exemplar comments that you can pull out. These comments are the documents that I just mentioned. So these are highly concentrated topic 1 documents. So these are exemplar comments. Topic 2, errors and failures. You can see this sort of comments that have a lot of this topic 2 in them. So you can see they tend to cluster these very different comments together in a coherent way. You can also look at those comments or the topics and the connections or the correlations between them and create a map of all of the comments in the 16,000 responses from the survey. And it gives, I think, a pretty good high-level description qualitatively of what's going on. You can also look at the prevalence of these topics and how it depends on the year and the rating. And so this is another data dilemma. So topic modeling tends to just give you that unsupervised machine learning view of how the documents and terms cluster. But you can also use this technique called structural topic modeling, a little newer technique that models how the topics are distributed according to covariates. So how the distribution of topics across comments is generally assumed to be uniform, but you can link it with structural topic modeling to covariates. And that's what we do here. So this is a picture of all of the topics in each of the little cells in this faceted diagram. And then across the horizontal is the rating from definitely would not to definitely would. And the vertical is the proportion of comments or proportion of the topic that describes those comments. So I'll just zoom in on a couple of them here. Hacking and glitches. You can see from the dotted line that the proportion of these topics was fairly constant. The distribution was similar in 2016, 2017, and I'll just zoom in on those. So hacking is something people worry about. This is one of the reasons why people definitely would not drive or ride in one of these self-driving vehicles. You can see the higher proportion of this topic with the responses where they said they definitely would not ride in one of these vehicles. Safer than human is another way that people see these vehicles. And you can see that this is one of the reasons why they definitely would. So some people have this in their comments, and those comments are associated with ratings of definitely would ride in one of these self-driving vehicles. So in this case, that you can think about these people thinking the other drivers are worrisome versus hacking and glitches in the self-driving vehicle being worrisome. So I'll zoom in on just two more of these here. Self-driving accidents and trust when mature. So here we see 2017 with across the board more comments related to self-driving car accidents. Not surprising, the Tesla crash in Florida got a lot of publicity. Then similarly, you see trust when mature. On the left, more higher prevalence of this topic for those saying definitely would not or would not trust being higher in 2017. So the topic modeling not only tells you why people like or would generally prefer self-driving vehicle or not, why they'd trust it, why they would not. It also tells you how that changes over time and gives you a sense of what are the factors leading to that change over time. Okay. And then the last one that I want to mention briefly is this control until proven. So this is one of the reasons why people resist self-driving vehicles is they like to control. And control, I think, is really important. And I'll just finish briefly by describing why I think this is so important. It has to do with dread risk. And dread risk is the perception of risk subjectively, not the engineering risk, but the subjective perception risk. And dread risk is 1,000 times greater than controlled risk. And so we see this in a variety of ways. And particularly if you look at how people judge risk of driving versus flying. Driving is way more dangerous than flying, but people see flying as more dreadfully risky. Dread risk is important because it guides decisions. So if we look at what happened after 9/11, people stopped flying, they started driving. There are more people killed in traffic accidents after 9/11 because of the increased driving than there were by the terrorist attack itself. Related to this issue of dread risk is the idea of understanding the behavior of the automation. And when automation behaves in unexplainable ways, it tends to be viewed as dreadful. And this is an example on the bottom right of a technology intrinsic to self-driving vehicles, vehicle vision systems, being able to see a stop sign. Without the little graffiti here, the stop sign detection was perfect. And with the graffiti, it dropped to 0. So a small change, hardly noticeable to a person, dramatically affected the automation. Not what people would expect, but would cause it, I think, to be viewed as dreadful in the sense of inducing dread risk. And dread risk is also accompanied by a loss of control. So dread risk is the risk that occurs when things are uncontrolled or unobserved. And people like having, so if you can have some degree of human input with a self-driving vehicle, it's likely to be trusted much more and less likely to induce dread risk. And we see this with elevators. So this is a picture of an elevator door, the closed door button that all of us use all the time. Here, it was just glued on to give us the illusion of control. And apparently this is the case with 85% of elevator door buttons. They're not hooked up. They don't do anything, but they make us feel better. So I'll finish with just a brief description of how this fits together. First, the basis of trust is not just direct experience. So the J.D. Power survey, none of those people had experienced self-driving vehicles, but they had already developed a sense of whether they would trust it or not. That will change based on experience with the system. So I think that's an important caveat to interpreting those data, that trust is grounded in experience and the dimensions of trust shift with the basis. So when you look at the societal, what society thinks, you might be grounded by more the purpose and the claims of the manufacturers and of the government about the safety of the system. And then when you experience it directly, it may be governed more by the performance. Okay? The sense of control that you have interacts with your experience with the vehicle to affect your perceived risk. So perceived risk is diminished by a sense of control. That sense of control, by diminishing your perceived risk, may lead you to rely on it more, and then you'll get feedback that could lower your perceived risk and then govern your acceptance, which feeds back into the experiential part where you then have a chance to experience it more, which then influences your trust. And this could be a vicious cycle or a virtuous cycle. So there's an importance of feedback there. So I'll finish very briefly with some work that we're working on with NASA. So this is new work with NASA where we're looking at how people interact, how astronauts interact with virtual assistants on deep space missions. So here we're trying to manage and measure trust in a virtual assistant by looking at how they speak to the virtual assistant, using conversational analysis to assess trust, and then use that to govern the conversational affordances with the virtual agent, and then induce maybe shifts in the virtual agent to repair the trust that might have been lost by the operator, or to temper the trust of the operator if the operator's trust is too high. So this is inspired by some work that was done by NASA with the leader of our project, Steve Robinson, who's an astronaut. And this picture I thought was just amazing. Steve Robinson, an astronaut that went up on the space shuttle just after the first shuttle launch after the disastrous tile failure, and they inspected the tiles and they found a problem, and Steve had to go out and repair the space shuttle tile in space. And this is the tool that he had to develop, build, and you can see the duct tape on the tool that he took out to do some cutting of some material that had protruded from the underneath of the space shuttle. So this is the sort of troubleshooting that astronauts, as they go to Mars, will have to deal with. And Manuel drew this little picture on the left showing this relationship between the astronaut and the agent that's to help the astronaut. To trust or not to trust is the question. And if any of you have seen 2001 Space Odyssey, you'll recognize how the intelligent agent that we're trying to help create a better, more helpful HAL. So with that, I'll just show you where HAL may stand with the automation and appropriate trust. So from the micro perspective of HAL working with Dave, trust dropped as HAL tried to do away with Dave and his crewmates. If you look from maybe a macro perspective, a societal perspective, HAL working for NASA, if Dave was getting in the way of the mission, maybe it's appropriate for HAL to act in the best interest of NASA and get rid of the human that was getting in the way. So a bit controversial about how technology should be advancing people versus organizations, and something, hopefully it'll provoke a question from the audience here about the role of people working with automation. So with that, thank you very much for your attention. I look forward to questions about HAL and Dave and trust between people and astronauts, or between people and their self-driving vehicles. So thank you.
Yeah. Thank you very much, Dr. Lee. So if you have any questions, you can either ask or type in the chat and I'll read out.
So,
oh,
I was just going to say, I have a request, I have a comment and a question.
okay.
I have, I have a Tesla, so I was following through almost every one of your slides. Well, first, the comment is that, first of all, thank you for visiting us virtually and giving an excellent talk. I wish we had the opportunity to sit down over dinner and ask you a few more questions over a longer and a more relaxed period, but of course, we'll try to do that another time. Yeah. I guess the request is, when you started talking, the presentation mode was not on, so we missed the first couple of slides. So my request is, I followed every other slide. I just don't want to leave feeling that I missed out the first two slides. So if you wouldn't mind sharing those two, you're talking about a building on your campus, I think, and I think the very first one or two slides.
Yes.
And then the question, while you're doing that, you mentioned, in 2016, the Tesla crash, the auditory and the visible signals were coming in. Yeah, was it this one? Yeah, that one. Okay. Yeah, I think I've seen that building. Yeah, that's a beautiful building. Okay. Then if you can go back to the slide where you had the Tesla crash, and when you were getting the auditory slides, I think you said every 6 minutes, but my experience, again, my car is, I bought it in 2018. I think it's like 15, 20 seconds. If I don't have my hands on the steering wheel, it'll give me both the visual and auditory sound. Was that not the case in 2016?
They do software updates
Yeah,
almost
every day
weekly.
almost.
Yeah, exactly. Which I think is a fascinating question from the perspective of trust, because the car that you had last week is different than the car you have today, and very different than this 2016 version. So they are changing things every week. And so this is the pattern of warnings that they had a few years ago. That's certainly different than it is today. And just recently, I think they've started using video to track the driver's face. And so they may start not just looking at whether your hands are on the wheel, but also whether your eyes are on the road, which I think is a really important thing for them to do. That's what GM does with Super Cruise. And I think in these sort of situations, monitoring drivers' attention and engagement is very important, and maybe more important than whether the hand touches the wheel periodically.
But, you know, the current technology, at least what I'm experiencing, probably puts me in the category of trusting it too much. So while you were presenting, I was asking myself, am I trusting the technology too much, right? But like you were saying, if I'm on a road and there's, the stop and go traffic, I trust the vehicle more than myself, partly because the vehicle can sense the deceleration, that's occurring in front of me better than I can. So, when I'm in a stop and go, I'm very comfortable just when I'm not changing lanes, putting it on, or even otherwise, I would say, but certainly stop and go.
Yeah. I think you bring up a really important point. When I was talking about a trust there, I was really lumping the experience together as a single homogeneous, every instance is the same perspective. But in addition to calibration of trust, there's the resolution of trust that's equally important. Does your trust change moment to moment with moment-to-moment changes in the capability of the automation? And I think that that's maybe more important, that people recognize the one instance where it's not handling things well versus having a general sense over the course of the next month whether it will behave well. I think it's the resolution that may be more important than the calibration to some degree.
Thank you. Appreciate it.
I have a question. First, I want to applaud the Bayesian analysis. Loved it. Thought it was great.
Yeah, I took out a slide proselytizing a Bayesian approach, but maybe I should have left it in. But anyway, thank you.
Well, I wanted to comment on the problem with the discrete response and magnitude. If you had seen any work, or if you thought about coming up with or deriving a joint prior distribution using both of those data sets.
Yeah. So with, as many of you know, with Bayesian analysis, there is the opportunity to define a prior distribution, and that can be really useful in a lot of situations. What we did here is just used an uninformative prior distribution. We didn't spend a lot of time thinking about how to specify the prior distribution. But that's definitely something that I think for this in particular and in general, people need to spend more time thinking about what should be a prior distribution. And one reason for that is that it allows you to make your analyses more sensitive by including information that is uncontroversial. So for example, with the vehicle, the accelerator pedal position or the acceleration a vehicle can achieve, you can put a prior distribution in that's based on the physics of the vehicle capacity. You know, a vehicle, unless you've got a Tesla, is not going to accelerate at 1G or more. And that is uncontroversial. Some of the other elements of the prior distributions get really controversial, and people complain about bringing in subjectivity to the analysis
Right.
and cheating. But yeah, so we just went with the flat, uninformative
Flat, yeah.
priors.
And then I had another question. I liked your comment later on that trust is not just a one-time thing. It's not instantaneous. It's a continuous concept. And so from the healthcare perspective, you know, over trust in a system, you know, over trust in a automated system where it's helping diagnose someone or come up with a treatment plan, the failure in over trust, that may not show up until weeks, years down the road, depending on what kind of misdiagnosis it was. That how do you quantify over trust in that kind of dynamic system, or how do you incorporate trust into the SEEPS model, if you will?
Yeah, I haven't thought about specifically how to incorporate it into something like the SEEPS model. I think this simple model here that I showed, or maybe kind of cluttered looking at it model that I showed, begins to get at that, I think.
Yeah, I noticed that because I had that question coming up in the middle of the talk, and I saw that diagram at the end, and I was like, oh, there that is. But I think that one thing that we should think about is, you know, what happens when the failures happen so far down the road, when we're looking at it longitudinally instead of instantaneously.
So I think part of it is on the left, where we have the basis of trust. You have the experiential trust. That's the moment to moment, what you're experiencing. Those experiences get accumulated into a relationship. So you can, over months, you have a relationship with your car that you develop, or a relationship with your physician, or the physician long-term develops a relationship with the decision aid that's helping. So I think that's part of it. I think there's another concept that is related to that, and that's a trust frame. And it's how you frame your trust in the system, whether you frame it as the system is generally good, I trust it, and that framing then governs how you interpret the experiential trust moment to moment. And it's almost like a Bayesian prior. Right?
Yeah.
And so I think long-term, with delayed feedback, you're forced, well, when you have delayed and imperfect feedback, you're forced to rely on your priors, right? And so you're forced to rely on that relational trust or your trust frame, and that can be good or bad. So how that trust frame gets defined and communicated depends in part on the societal relationship to the technology, whether society trusts it or not. And I think because of the difference in time constants between how society learns to trust self-driving vehicles or decision aids in the hospital, that's even more delayed than the relational trust. And so figuring out some way of shortening the time constants to identify problems with the automation is a tremendous societal challenge. Like, how do we identify the problems and communicate it so that biased algorithms don't proliferate and get caught? If you haven't seen Kathy O'Neill's book, Weapons of Math Destruction, I would highly recommend it, because she talks about these sorts of problems. And I sadly don't have a great answer other than to say it's the delayed feedback is a problem from control theory as well as societal individual adaptation to technology. So
great. Thank you for that answer. My research students are working on trust and automation in primary care, so they should be intently listening right now.
Well, I have a minute here. This is dangerous. But let's maybe do something dangerous here. I'll try to bring up another slide to finish on. And this is from a paper. It's a paper that I just spent like 20 hours this weekend working on, changing to the annoyance probably of Aaron Chu, who is the co-author on this paper. But your students might find it useful. So it's accepted as human factors, and I can share a copy of it if you or others are interested. And the thing that might be interesting is this model of trust that has a couple distinguishing features. Hopefully people are seeing this.
Yeah.
So on the top is the human agent, the bottom is the automated agent, and then you have these influences and signs, how they communicate back and forth through some sort of interface. But then there's also actions and observations on the situation, on the world. And the situation may have a goal structure that's different for the automation as opposed to the human. And so there's potential for goal conflict in a prisoner's dilemma sort of fashion there. And those interactions on the world feedback in terms of the interaction outcomes to the person and to the interface between them. So I think this might be a useful way of thinking about those sort of dyad relationships between human physicians and the automation they interact with. And for the HAL-like automated agent that's supporting the astronauts on their mission to Mars.
Yeah, I like this diagram. Even like that the humans on the top, because humans are going to naturally take a top-down processing approach. Automation's on the bottom.
Yeah, but in the paper we talk about what happens when the reverse happens. And this is a scary thing in current work environments like warehouse pickers for Amazon. The automation is on top in that the robots are now controlling the people as if they're robots. So the AI is controlling people and using people as robots because the roboticists haven't developed manipulators like as facile as the human hand. So the people are the effectors for the robot brain and being used as such, and it's kind of terrible. So I think there's the potential for the automation to take control and flip it from the people being on top and supervising the automation to the people being subordinate to the automation. And this is not only in the warehouses, but also in knowledge workers, where you can monitor people's keystrokes per minute, your graduate students, how many words per day they're producing, and then have that automation tell them when they can get up for a break and when they can't. So I think that this dynamic between the automation and the person or the agent is going to be something to look at going forward. So.
Yeah, definitely. Thank you.
Well, thank you all for being part of this. And thank you very much, Dr. Lee, for having taken time off your schedule to present this to us. So the conversations can continue after this seminar. And of course, we've recorded it, so you can always go back to it and watch. Thank you and have a very good rest of your day. Okay, bye-bye.
Thank you all. Bye.
Bye.